And we return. So, continuing from where we left off, we had just finished talking about Boyle's law, which talks about the relationship between pressure and volume for a sample of gas at constant temperature. And here we come into Charles's law, or Gay-Lussac's law. The name can flip back and forth between the two. One of them was more famous, the other one discovered it first, so... And they didn't even really fight over credit. It's just that the more famous one said, look, that guy discovered it first, give him the credit. And people mostly did. But still, you can find it under both names, depending on where you look. So these two, an Englishman and a Frenchman, they discovered independently that if you have a sample of gas and you increase temperature, you decrease volume. Decrease temperature, you increase volume. I mixed that up. Increase one, increase the other. Decrease one, decrease the other. Notice what is missing here. Pressure. You're holding pressure constant for your sample of gas. So look over here on the right, and you'll see, your cylinder with the gas, the piston pushing down on it. The piston is the same in the two cases, the left and the right. So what they're telling you is that the pressure is staying constant. Okay, the external pressure isn't changing. So when you increase the temperature of the gas, you increase the volume of the gas. You decrease the temperature of the gas, you decrease the volume of the gas. So that is the straightforward explanation of what Gay-Lussac's law is. But we also have the math and the kinetic molecular theory explanation for the law. So let's go ahead and first dive into the kinetic molecular theory of it. Let's say you have a sample of a gas at a certain temperature, certain volume, certain pressure. Let's go ahead and explore what happens when you increase the temperature. Now, we know, look over here at the chart on the right, left-hand column, you increase the temperature, you're going to increase the volume. The question is, why? So you start at your initial cold temperature, T1. What's going on there? Well, the particles of gas inside this piston, the cylinder with the piston on top, they're moving around at a certain speed, because temperature is a measure of the average kinetic velocity of the particles of the gas, or of any substance. So they are moving around at this cold, slowish temperature. They're striking the walls of the container with a certain amount of force. The sample has a certain volume. That means a certain area inside the container. Force over area. That gives you the initial pressure of your system. Now that pressure is being exerted in all directions on all the walls of the container, including the piston up top. Now what's it pushing against? In the case of the walls of the container is rigid. The walls are fixed, so it's pushing against the container itself. But the piston is not rigid. It's not fixed. It can move around. So it's being held in place by the air outside of the cylinder. Okay? And we're talking about our initial conditions, and we assume things are stable until we come in and start screwing around with it. So that means that the piston was staying perfectly still, which means that the forces on either side of the piston have to be balanced. And the reason the piston isn't going anywhere is because the pressure on the outside is equal and opposite. It's also P1, our initial pressure. So what happens when we increase the temperature of our sample? Well, for starters, higher temperature means that your particles are moving a lot faster. And if your particles are moving a lot faster, that means they're going to be hitting things with a lot more force. But initially, our area hasn't changed, our volume hasn't changed or responded yet. The area stays the same, so we have a higher force over the same area. That means that it's exerting a lot more pressure, including on the piston. So we're looking at a disequilibrium. Okay, the pressure inside the piston is now greater than the pressure outside the piston, which means that the piston is going to have to shift. It's going to have to move in response to this change in pressure, and it's going to move outward because the pressure inside is greater than the pressure outside. Now, as the volume inside the cylinder increases, that means the area inside the cylinder is increasing. And if the area inside the cylinder is increasing, that means that the pressure is coming down. It's decreasing because force over area is equal to pressure. And eventually you're going to get to a point where the pressure inside is equal to the pressure outside. Okay, you've reached your new larger volume. Okay, the pressure is reached in equilibrium. The force is still higher, but a larger force divided by a larger area gets you the same pressure. Okay, the pressure hasn't changed. Pressure has to stay constant. Now, in reality, you wouldn't see a sort of stepwise function like this. First increase temperature, then increase force, then increase area. Okay, no, instead, you put in energy, the temperature changes over time, and the force immediately changes in response to that. The volume immediately changes in response to that, keeping the pressure at equilibrium the entire time. But when you're dealing with state functions like this, temperature, pressure, force, area, these are all state functions, you can sort of pretend, you can reduce it to this stepwise procedure and pretend. Now, the work and the heat, those are not state functions, so the heat that you have to put into this cylinder to get this temperature change, well, that's going to change depending on how quickly or how slowly you put the heat in, and the amount of work that the piston does as it expands outward into against atmospheric pressure, the amount of work is going to change as well. So you can't deal with those in the same way that you can temperature, volume, and pressure. So we don't. But as you increase temperature, you increase the force exerted by the particles. Now, that force is going to stay the same the whole time, more or less. Okay, increasing temperature is going to increase force, and you're not going to bring that force down until and unless you reduce the temperature again. But what is changing is the area inside the cylinder, and force over area is pressure. So increasing temperature means increasing force, and the volume of the cylinder has to change in response to that because it's being held as it is. It's being maintained by the external pressure. The external pressure is not changing, so the volume shifts in response to that. And you get a similar change for similar reasons in the other direction. When you decrease the temperature, this causes a decrease in the speed of the particles, which means that there's a decrease in the force being exerted by those particles. So the pressure inside the cylinder decreases. Now you have a disequilibrium in the other direction. The atmosphere is pushing harder than the gas inside the cylinder is. And so the piston will come down, the volume shrinks as you decrease your temperature. Now let's go ahead and take a look at it from the other perspective. How does temperature respond when you change the volume? If you are familiar with diesel engines, stop it. You're going to screw yourself up there. Do not think about this in terms of diesel engines, not yet anyway. You have to think about this sort of sideways. It's like walking through a corkscrew. Okay, what happens when you decrease the volume? What happens to temperature when you decrease the volume? Well, you have to remember that the system is being maintained at constant pressure. But in this case, you have to think that you're changing the volume, so you have to do something to the temperature in order to keep the pressure constant. The system won't necessarily do it itself in this case. But pressure is staying constant, and pressure is equal to force divided by area. So that means that force over area has to stay constant as well. If you're decreasing the volume, that means that you are decreasing the area. If you're keeping that ratio constant, that means you also have to decrease the force. And the only tool you have at your disposal for decreasing the force exerted by those particles is the temperature. You have to decrease the temperature. So it's kind of wonky. You have to come at it sideways in order to think of it in these terms. Instead of the system responding naturally to whatever you're doing to it, you have to think about what you have to do in order to keep things from spiraling wildly out of control. But if you decrease the volume, that means the temperature has to decrease as well. if the system is going to stay at constant pressure. That constant pressure thing is key to keeping things from getting all screwy. Okay? A big part of thermodynamics work and things like that, if you go on to keep studying thermochemistry, chemistry in general, long enough at least to get to physical chem, is if you really have to pay attention to the conditions that your system is operating at. Pressure, temperature, volume, what's constant, what's not. It can get a little bit annoying. I mean, you think me yelling at you in lab about wearing your goggles is annoying? You ain't seen nothing yet, all right? But those are that's all I really want to go into for KMT, for the kinetic molecular theory explanation of Charles's law. Let's look at some examples of math problems. Now, starting general and moving to the specific, Boyle's law, as you'll recall, says that pressure and volume are inversely proportional. As pressure goes up, volume goes down. Or, to put it another way, pressure times volume is constant. P1V1 equals P2V2. Charles's law, or Gay-Lussac's law, is different. It says that volume and temperature are moving in the same direction. They are directly proportional. You increase one, you increase the other. Decrease one, you decrease the other. Or their ratio has to remain constant. V divided by T is equal to a constant. Or, in the mathematical terms, V1 over T1 equals V2 over T2. So that means that if you double volume, you have to double the temperature. And if you cut the temperature in half, you cut the volume in half. So that sort of ratio problem is fairly simple, fairly straightforward. I might throw a couple of those at you on the test. But let's look at something that is a little bit more like a traditional math problem, a word problem, as it were. So let's say you have a 255 milliliter sample of gas at constant pressure and 375 Kelvin. Now, if you were to increase the temperature of that sample to 490 Kelvin, what would happen to your volume? Now, let's go ahead and rewrite this in terms of the mathematical equation, Charles's law, Gay-Lussac's law, V1 over T1 equals V2 over T2. So, looking at our problem, we see that we're going from 375 Kelvin to 490 Kelvin. We're starting at 255 milliliters. We don't know what volume we're ending up at. We have V1, we have T1, we have T2. We're looking for V2. So we go ahead, we do a little bit of algebra, and we come up with volume 2 equals volume 1 times T2 over T1. And just a little bit of rearranging there. Now we sub in our the values that we know, V1, T1, T2. We get 255 milliliters times 490 Kelvin divided by 375 Kelvin. The kelvins cancel out. That leaves us with milliliters. Okay, so our units are going to be milliliters. We're looking for volume. Our units are volume. That's good. We do a little bit of math on the calculator, and we find that the final volume is 333 milliliters. That is a nice, simple example of a Charles's law problem. Okay, we are running up on the 15-minute mark, so I'll go ahead and call it an evening for this lecture. When we come back, we'll start in on the next of our collection of gassy gas laws.